So we can cationic ionic acids. What are these? Positively charged. So these are positively charged species that can donate a proton. Okay, examples of these cationic acids are NH4, yeah, ammonium ion, hydronium ion, and H4 plus, H3O plus. What else? CH3OH2. All right. Okay, now we know the Bronsted-Lowry acid-base theory, cationic acids. Then, let me delete this. What are the factors affecting acidity? Acidity of cationic acid. Factors affecting acidity of cationic acids. So we have to know this before we can assess the relative acidity of. Okay, so what are these factors? Okay, electronegativity. Okay, the first one is charge density. Is it included there? Because I just didn't, I only read a few from the ones you sent me because it has a lot of words and it's confusing. Okay. Okay, so we will just do this. So factors affecting acidity of cationic acids, one is the charge density or electrostatic attraction. Okay, so a higher positive charge or smaller ionic radius, this one increases polarization of the acid acid hydrogen bond or the oxygen hydrogen bond in hydrated ions. Okay, familiar with that? So this one makes it easier to release hydrogen proton or H plus. So makes it easier to release H plus, increasing acidity. Okay, so you got that? So one of the factors is the charge density or electrostatic attraction. So the higher positive charge or the smaller ionic radius, that means it makes it easier to release H plus, therefore it has higher acidity. Higher positive charge or the smaller the ionic radius, the easier it is to release the H plus, then the acidity increases. Okay, like let me give you an example. Okay, example. Yeah, I'm writing an example here. That's not only the factor in that affects the acidity of cationic acids. Like what you said, we have the electronegativity. Negativity of the central atom. Yeah, so the more electronegative the central atom is, so a more electronegative central atom holds on to electrons more tightly making the bonded hydrogen more positive and easier to lose. So like say for example, you have ammonium ion and then pH 4 ion. Nitrogen here is more electronegative, right? Therefore, NH4 plus is the stronger acid. And then the next factor is, okay, we already have, what are those? Electronegativity, the electrostatic attraction, and then the third one, what's that? The other one, size of the central atom. So it also affects size of central atom. This is for hydrated ions. Yeah, right? Hydrated metal ions. So size of central atom, smaller cations like aluminum ion or iron ion, they create stronger attraction to water molecules, right? Stronger attraction to water molecules, then polarizing them more, they're more polar, leading to acidic behavior in water. So smaller cations, more acidic, larger cations, has lower charge density, meaning weaker acidity. Yeah, so you just take note of that. Smaller cations leading to acidic, more stronger acidity. But larger cations have lower charge density, which leads to weaker acidity. Say for example, barium ion, calcium ion. And then the next factor is resonance. Resonance and what's this? Inductive. Is this included? Resonance and inductive effects is in the list. This is for organic cations. Okay, so it has something to do with the nearby electronegative atoms or groups that can stabilize the conjugate base, right? Like say for example, you're given NH3 ion. So in this cation, the nearby electronegative atoms or groups that can stabilize this, or the conjugate that can stabilize the conjugate base. This would enhance acidity, so it's more acid, stronger acidity. Okay, then I think those are the only factors that can affect the acidity of cationic acids. All right. Okay, so let us summarize this one. Let's say for example you're given H3O plus. What is the conjugate base of this? So this is your cation. So you need to know the conjugate base. Yes, conjugate base of this one is water, and its relative acidity is very strong. Why? Reason. It has high charge density. Why it has high charge density? Because it readily donates H plus. So if it readily donates H plus, it has high charge density, therefore its relative acidity is very strong. Okay, how about NH4 plus? What is the conjugate base of this? Okay, NH3. So nitrogen is, what is this? Which one is more electronegative, nitrogen or oxygen? Okay, oxygen is more electronegative, so therefore N is less. It's still acidic, but not that really strong. Okay, so you can say like moderate, moderate relative acidity. How about Na plus? It doesn't have a conjugate base. Does it have a conjugate base, the Na sodium ion, cation? No, so it doesn't have. That means it cannot donate, can't donate H plus, and therefore this is not acidic. So you just have to take note that for cationic acids, acidity increases with positive charge and a smaller ionic radius. Let me just write down the summary here. So acidity of cationic acids increases with, okay, so increasing positive charge and smaller ionic radius, then increasing charge density or larger charge density, meaning more acidic. Yeah, more positive, smaller radius, larger charge density, then more acidic. Higher positive charge increases acidity, smaller ionic radius increases acidity, higher electronegativity increases acidity, electron donating groups decrease acidity if you have electron donating groups, and stabilized conjugate base, that one increases acidity. Okay, so we're good with this, the Bronsted-Lowry, no problem with this. And then the second page, it's the same. And then the third one and the fourth one. So the third one, it says predicting the position of equilibrium without using pKa values. And the second one, without using pKa table, predict the position of equilibrium for the reactions. So how do we predict that? How do we predict the position of equilibrium of reactions without using the pKa table? So the Bronsted-Lowry acid-base theory is still useful here. Okay, can I delete this? Predict the position of equilibrium. So let's recall the acid-base reaction. So if we have acid 1 plus base 2, okay, so we produce base 1 and acid 2, right? So equilibrium favors the side with the weaker acid. Equilibrium favors the side with the weaker acid and weaker base. All right, so this means that proton transfer goes from stronger acid to the stronger base, producing weaker species. So proton, let me just write that down. Proton transfer goes from the stronger acid to the stronger base, producing weaker species. All right. Okay. So we've already recalled the acid-base reaction. So now we need to know how to decide which acid or base is stronger without using the pKa table. Okay, so let me delete this. How do we do that? There are factors. I think this is it's based on the molecular structure. You're given the molecular structures, right? Can you? Yeah, that one. Yeah, we're given the molecular structure there. So we can reason qualitatively from molecular structures using 5 main factors that can stabilize the conjugate base. If we stabilize the conjugate base, therefore, it makes the acid stronger. Got it? So we have 5 factors here. Okay, the first one is the atom. So what are we going to compare for atom? The molecular structure. Yeah, you will look at the atoms first. Yes, the charges. So the atom bearing negative charge in the conjugate base. So you compare that. Which one is your conjugate base? Across the period, more electronegative atom, stronger acid. Let me just write that down. So atom, yeah, yes. So you need to compare the atoms, the atom bearing the negative charge in the conjugate base. Okay, more electronegative, stronger acid. Down a group, larger atom, stronger acid. And then the second one is resonance. How do you identify resonance? Okay, like you need to compare if the conjugate base delocalize its charge. Can the conjugate base delocalize its charge? So more resonance, more stable conjugate base, meaning stronger acid. Okay. Then I think also the hybridization, the charge, inductive effects, they are also the factors. Okay, so inductive effects, are there electronegative atoms nearby pulling electrons? Then hybridization, what orbital holds the negative charge? Yeah, and then the charge, compare the charge versus the neutral acids. So positively charged acids are stronger than neutral. Neutral acids are stronger than negatively charged one. Then you can decide equilibrium direction. So identify the acids on both sides. So which ones there are acids? Is the stronger acid. So that one is an acid. Okay. Yeah. So the equilibrium favors the side with weaker acid. So which one there is weaker? Okay, which one there's nitrogen? The acid, the stronger acid. Okay, so that one is your acid. What's this? That one has the conjugate base. Yeah. So the one whose conjugate base is more stable, then that one is stronger acid. Yeah. So which one there is stronger acid? I'm confused with that. Can you zoom in a bit? What's that? HCH2 H2OH. Okay. The reverse reaction is favored because, yeah, if products contain, so it'd be easier, contain weaker acids, weaker acid, then equilibrium is to the right, forward to the right, so it would be easier to understand. Then if reactants contain weaker acid, then equilibrium is to the left, meaning reverse reaction. So it would be easier to identify. So first, okay, first thing, you identify the acid-base pairs first on both sides and determine which acid is stronger. Yeah. So which one there in that reaction? That is CH3, CH2. So which one is stronger there? Which one has a weaker acid? The product side or the what's this? The reactant side. Okay, CH3, CH2 minus. So it's ethyl. That one loses a proton, right? It loses a proton when you have water. So it should go forward. Okay, forward. Well, you have two forward there. Forward reaction is favored because oxygen is better. The other one is making the base on the product weaker, making the base on product stronger base, meaning the products contain weaker acid. Yeah. What else do you have there? Those are all practice questions for organic chemistry. So, okay, we check on the possible functional group types for this. C4H12O2. So it has 2 oxygens and 1 degree of unsaturation. So possible functional group types of this: COOH, carboxylic, and ester RCOO. So possibly aldehyde, right? Aldehyde alcohol or ketone alcohol. So let's try the constitutional isomers. So we have carboxylic, COOH. So it can be an acid. We can try that, CH3. So we can say CH3, CH2, CH2, COOH. Butanoic acid. And then what else? CH3, 2CHCOOH, or what's this? 2-methyl. How many carbons? Propanoic acid. Yeah, you need yes, but the problem is you need to draw, because that one is in skeletal formula. So I'm just trying to write down the constitutional isomers of that one, C4H2O. So possible butanoic acid. Then the second next one is 2-methyl propanoic acid. Can be. And then we have methyl propanoate. Then ethyl acetate. So which one's there? If you're going to draw that in a skeletal formula using the structure of that. So the first one is butanoic. So you can draw that as this one. Maybe how many carbons? 1, 2, 1, 2, 3. So you have oxygen here, and then alcohol. That one, and then the other one. We have 2 methyl propanoic. So how do you draw that? Methyl propanoic. Yeah, the second one. You can. Does it have OH? Yeah. Or you can do like this. Draw oxygen, CH, OH. Okay, the second one. And then the third one, methyl propanoate. Which one there is methyl? It's not in the choices. So methyl propanoate would look like this. We have oxygen. It doesn't have. Okay, but we have the first two. And then the other one is ethyl acetate. Ethyl acetate. We don't have there. So ethyl acetate will look like this. So it's not there. So I think the first two choices only. So can you click if it's correct? Whether it's correct. Okay, which one there is? Okay, let me. Okay. So we have 4, right? 4 constitutional isomers. And in the first one, we chose 2, the butanoic acid and 2-methylpropanoic acid as more acidic, right? 10 times, trillion times. And the second one, less acidic. So we choose there the ones which are esters. I think esters. Esters, the methylpropanoate and ethyl acetate. This one. The third and the fourth one. So they are least acidic than the carboxylic. So which one's there? So this is the skeletal formula of methylpropanoate. And this one is the ethyl. This one is the ethyl acetate. Which one there? Acetate. I don't see in the choices. And this one is the methyl propanoate. This one. That one is the ethyl acetate. So from the choices, I don't see that. C4H9NO2 NO2. Okay. 3 of these isomers have similar pKa values. While the 4th isomer has a much higher pKa value. Identify isomer with the highest pKa to determine, I think. So, without the pKa table and only given the skeletal structures, the major determinant of the COOH pKa is the inductive electrostatic influence from positively charged or ammonium group if you have there. Yeah. So you need to identify which ones are alpha and beta amino acids. So alpha amino acids that means it has lower COOH pKa. And then beta and gamma isomers, which have like 1 or 2 carbons farther away, so it's weaker. COH is weaker. Yeah, I hope, but it's there. So you just have to predict the relative picture by ordering it. So COOH acidity, strongest to weakest. Then alpha isomers is greater than the beta and gamma. And then we have the NH3 plus acidity, pKa of ammonium lower. The pKa of ammonium is lower, means easier to lose hydrogen or proton. So alpha isomers tend to have slightly lower pKa than beta. So so you need to identify which ones are alpha and beta. Isomers have lower pKa than beta or gamma isomers because of the positively charged NH3 plus. Yeah. Yeah, I forgot I have another student.